Alright, well this is my Physics 114 project. My name is Ashley Looper. My sound was L. Let's go ahead and jump into it. So the first question was, what are the fall times of the objects? I went ahead and calculated the times and measured them by using the Logger Pro on the computers in the lab room and adjusting the scale so I could measure the change in time between the impact spikes. What is the error in my time data? The error in my time data is minimal. This is because I was able to utilize Logger Pro to obtain the most accurate change in impact times, because I was able to change the scale to zoom in as far as possible. This error is also based off the assumption that Logger Pro was an accurate representation of the impact time intervals given. So I went ahead and chose my time error to be about 0.01 seconds. I based this off the scale that I chose to zoom in on Logger Pro. What are the heights above the floor for my objects? I went ahead and used this formula here, h equals 1/2 gt squared. My first object fell about 0.483 meters. My second object fell 1.055 meters, and my third object fell 2.057 meters. The assumptions that I made when calculating the heights of the three objects were that I assumed the acceleration of gravity is 9.8 meters per second squared. I assumed that Logger Pro accurately recorded the impact noises from the YouTube video that we used. I assumed that the YouTube video was unobstructed and it was an accurate representation of the impact times that I was given. I also assumed that my time measurement is accurate because that was a hand measurement that I did go in and make the decisions on where to measure it from. The uncertainty in my heights are based off my time error, and this is because the equation that I used to find the height of my objects, I needed to use time in that equation. If these objects were dropped on the moon from the same height, their times would be as shown. Since the moon's gravity is 1.622 meters per second squared compared to Earth's 9.8 meters per second squared, when the objects are dropped from the same height, their fall times are longer than they would be on Earth, and this is because of the difference in the acceleration of gravity. If these objects were dropped on the moon and they had the same fall times, the way that I went ahead and calculated the heights that they were dropped from is using h equals 1/2 gt squared, and their distances fallen are much smaller than they would be on Earth, and this is because of that difference in the acceleration of gravity on the moon compared to here on Earth. If I only knew my object's impact times and not the release times, this is how I would kind of figure out how far they fell. I went ahead and decided to add and subtract 0.20 seconds from the original impact times, or to the original impact times. So here you see my original impact times, my impact times plus 0.2 seconds, and my impact times subtracting 0.2 seconds. These are the distances that my objects fell after adding those 0.2 seconds. I went ahead and used, once again, h equals 1/2 gt squared. When adding 0.2 seconds to each of my impact times, my objects' heights also increased. So, very interesting. And when I took away 0.2 seconds from the impact times, my object's heights also decreased. So, what happens to the impact times if all the objects were raised or lowered 0.10 meters. Here I have a table showing my original heights when I add 0.1 meters and when I take away lower than 0.1 meters. So if I went ahead and raised my objects 0.1 meters, their impact times would also increase. And if I lowered my objects 0.1 meters, my impact times would also decrease. So, is there a practical limit to the height increase that allows you to predict the fall times with your assumptions? The way I decided to answer this question is by simply stating that when the objects are dropped from a height where they reach terminal velocity, the equations would no longer be accurate because the equations do not consider air drag. So I guess I would be able to predict the fall times up until the point where they reach terminal velocity. So in another link, you will have my video of me performing the experiment. And I thought it was really interesting because my experimental data is within my time error that I decided at the beginning of this project. I think that my supplied data is obviously more accurate because during the experiment I noticed while watching the video back that I didn't actually drop the string until after I said drop. So I went ahead and adjusted the way that I measured these times to be an accurate representation of when I did let go of the objects. So we can see here that it had about 0.1, 0.1. So it looks like maybe my experimental data is about 0.1 seconds off. So if I were to drop these objects in an elevator that is accelerating upward at a half g relative to the ground, I went ahead and made this little diagram that you see here in the bottom right, pretty much just showing Newton's second law, in that it would be a very similar equation to the one I used earlier in the slideshows, except gravity will now equal 14.7 meters per second instead of 9.8. So there's that, and then here we have if the objects were dropped in an elevator accelerating downward at half g relative to the ground. Once again, I have a diagram with Newton's number 2 in the y direction, showing that I would be using 4.9 meters per second for gravity. So recreating the experiment, I decided to utilize my technology that I have given, and when looking through my phone and kind of trying to decide how I wanted to measure the time intervals between when my objects dropped, I found that the simple recording app that's provided for your phone called Voice Memos, I was able to kind of manipulate it in a way where I could really recreate Logger Pro, but at home for free. So I went ahead and used sewing thread because I wanted to use a string that was just really light and wasn't going to give me too much extra weight or air drag. And I measured started by measuring my full distance, and then I measured each of my distances between each of the individual objects. And I went ahead and used really similar sized beads, shape and size, so that wouldn't hopefully impact the experiment too much. Next, I measured 2.057 meters from my floor, and I went ahead and marked that on my wall with a sticky note, and found out that I don't actually need to be on a chair to drop these objects because I fell the first time while recreating this experiment. I then set up my iPad and decided to visually record myself performing the experiment with that device, and I had my phone set up right where the objects hit. So on the right here you can see the spikes at where each of the objects hit and where I say drop. Like I said before while watching the video, I didn't actually drop my objects until I finished saying the word drop, and then after the third spike you can actually see the echo spikes, but it was very clear to me. I did this about 3 times, just to make sure that I was measuring between the correct spikes. So here we have the time of impact from my experience. So the first square that you see here on the left is when I dropped it. Then I have the cursor on where I measured my data from. So then I have T1, T2, and T3. And I went ahead and did some math there and found the delta T, the change between T1 and T2, or T0, T1, T1, T2, T2, T3. And then I went ahead and found those times from T0. So, yeah, I believe that is my entire presentation. I hope that you enjoyed my PowerPoint. I know that you're watching a lot of these. Although it was a stressful project, I really did enjoy recreating this, and I hope that my voiceover is acceptable, because it's really nerve-wracking for me to be doing this. But thank you so much, and I'll see you tomorrow.